Vale. So, okay, so we continue now with Kalman, and what we have now is alpha determinations, but not from tau, but from E plus, E minus, no, I guess?
Yeah, so this is sort of really like part 2 of Santi's talk. It'll be, the first part I'll talk about another finite energy sum rule determination of alpha S, which is from electroproduction data, and there's new databases for that that allow this to be done. But then because of the fact that there's no kinematic constraint on what the hadronic invariant mass squared can be in E plus E minus to hadrons, you can actually use the R data in order to test some of the assumptions that are made in the older analyses in the tau decay, and that'll be the second half of the talk. These are my collaborators, so Santi, Martin, Diogo on the KNT RS collaboration for the first part of the talk, and then the second part of the talk, the KNT people are not responsible or guilty, whichever your attitude is. And these are the relevant papers. Okay, so Santi's actually set up most of this, but I'll just quickly go through this anyhow. So both the tau and electroproduction determinations of alpha S from sum rules are based on the same Cauchy theorem or finite energy sum rule relation, which Santi already explained. You start off with a kinematic singularity-free scalar polarization, which in the electroproduction case is the electromagnetic current polarization function, or in the case of the analysis Santi just talked about, the isovector particular spin combination of the scalar polarizations in vector axial vector channels. You have a spectral function, which is the imaginary part divided by pi of this on the Minkowski axis. In both cases, this is measurable experimentally. For electromagnetism, it's because R is proportional to the spectral function, and Santi showed you what the differential distribution, how it's related to the imaginary part of this already for tau. Here, W is any function that's analytic inside and on the contour in order that it just has this simple form with no additional.
Can you adjust the microphone? I can't hear.
Oh, sorry. Is that better? Okay, so these things for both those cases are measured experimentally with, in most parts of the kinematic region, pretty high precision. This is just something that you get to choose. This is something you get to choose as well. It's just the radius of the contour. And Santi already discussed in some detail that you can represent this. This is, of course, just a definition of what you mean by the duality violating part. The key thing is that this is up to exponential corrections for large Euclidean Q squared. It's a good representation. But because of the fact that when you're integrating around here on this side of the equation, you have contributions from near this point here where duality violations are not small here. You have to worry about this, and you look at the spectral distributions from experiment, and it says that they're indeed not small, as Santi showed. And so we'll come back to that later. Now, the OPE contributions that go into these analyses involve dimension 0 and higher. The dimension 0 series is known to 5 loops, which is order alpha s to the 4th, and we use that. Perhaps this is related to the last question. The dimension 2 in the terminology that's used in the literature here are just the mass-dependent perturbative contributions. So they're proportional to the light quark masses squared. These are all numerically negligible for the isovector tau sum rules, including the order alpha s squared ms squared strange mass-dependent parts. There are small, not entirely, but still having a small impact on the final alpha s, order ms squared contributions in the electromagnetic sum rules with no additional powers of alpha s. And in the EM sum rule analysis, we also included the first order electromagnetic corrections in the OPE. Higher dimension contributions are parameterized in terms of some effective condensates in this particular form here. These condensates are typically not known, so Dimension 4 includes the gluon condensate, which of course has a renormal on ambiguity. Then there are higher dimension condensates which enter, and which ones enter depend on which polynomial you have. So here I'll be, like in Santi's talk, just talking about polynomial weights, and then which condensates enter the theory side of the sum rule depend on the degree of the polynomial. So if the polynomial has degree n, you get OPE contributions up to 2n plus 2. So for example, if you just look at the expression for the tau width, which involves the kinematic weight of degree 3, that's why you get contributions up to dimension 8. Now, a couple of qualitative features that are relevant to keep in mind in assessing, basically, is the argument about how you treat non-perturbative contributions relevant or not. First thing is, this is just a rewritten version of the expression that Santi wrote down, which tells you about the relation of the fractional error at mz squared to that at some lower scale, at some lower scale where you did your fit, such as maybe the tau mass squared. And it tells you that when you go from a low scale to a high scale, you get a compression of errors that goes like the ratio of the couplings at those two scales. And so, for example, when you do a low scale electroproduction or tau analysis, it's something like the tau mass scale, this ratio here is about a third, and that's why you get a sort of a third level, factor of 3 improvement in the relative errors by working at low scale. So that tells you there's an advantage to extracting alpha S from a low scale analysis in terms of your final fractional error here. But of course you pay a price because you can't just go down to arbitrarily low scales in order to make this factor as large as possible or as small as possible, because eventually you run into uncontrolled non-perturbative effects. And the issue is there a sweet spot for this? Now this is particularly relevant for sort of, I don't know, simple technical reason, namely that it's true that the OPE contributions, when you look at them, are dominated, as you'd expect, at scales of order 3 GeV squared around m tau squared, which is much bigger than lambda QCD squared, by the dimension 0 part. But the integrated dimension 0 contributions have the following form. There's some constant that depends on which weight you've chosen. The first two terms in the expansion are 1 plus alpha S over pi, and then the higher order contributions have some weight dependence. Now, the point is that around the tau mass scale, this is about a tenth. So it's only about a tenth, and then with higher order contributions, there's a sort of factor of 6 between the actual alpha S dependent parts and the overall dimension 0 part. And so you might think, oh, I want to know alpha S at the tau mass to 3% so that I have it at 1% at the Z mass. And you might think, oh, that means I need to have control non-perturbative contributions to the OPE side at 3%, but it's not true. You need to control them at 0.5%. And so we're in a precision game, and therefore it's not good enough to control non-perturbative contributions by waving your hands. Okay, so now amongst the new non-perturbative contributions are, of course, duality-violating contributions. And as Santi mentioned, there's an old argument by Poggio, Quinn, and Weinberg that tells you that at sort of intermediate Q squareds, so Q squareds that are maybe fairly larger than lambda QCD squared, but not yet asymptotic, you expect the duality violations to be localized to the vicinity of the time-like axis. And Santi actually discussed this quite explicitly in the questions there. As Santi also pointed out, you can rewrite the duality violating contributions to the theory side in an alternate form using the imaginary part of the duality violating contribution to the polarization that involves the contributions from that between the point that you stop your integral on the experimental side and infinity. So it says you have to know how this behaves at larger S. The advantage is that if you have large enough S naught, there is an exponential damping of this. So eventually, at sufficiently large S naught, you would be able to neglect duality violations, but what that S naught is something that data has to tell you. Santi also mentioned that we looked into this and found that the asymptotic form for sufficiently large S, again, what that means you have to see from data, for these duality violating spectral contributions looks like this, an oscillating factor exponentially damped, with the exponential damping sort of determined by the structure of the large excitation part of the spectrum. crucial thing in terms of these issues of can I go to large enough S0 to be able to drop this is that in tau, you're not free to be sure that you're doing that because you're kinematically restricted to a maximum invariant hadronic squared mass, which is m tau squared. And so you certainly can't have S0 any greater than that and still be integrating data on the data side of the sum rules. That's a big advantage for the electromagnetic sum rules because the invariant mass is unrestricted. That's also the fact that the duality violating exponential damping of the spectral contribution, that it's exponentially damped also means that electroproduction sum rules in principle have an advantage for suppressing duality violations. Now, in terms of looking at experiment to see, can we really sort of say, oh, I think we're already at high enough scales to ignore duality violations. Again, Sandy covered some of this, so I'm going to go pretty quickly. But I want to emphasize also what Sandy talked about, which is often what's done is to say, let's look at the vector plus axial vector spectrum, because if I plot, and this is the Aleph data here for that spectral function, if I plot that versus the hadronic invariant mass squared, it starts to look fairly flat and similar to perturbation theory. And if I have a similar thing for the vector channel alone, and I'll show you a version of that later, then the wiggles are larger. And so it's sometimes argued this looks flat enough that surely I can just ignore duality violations. Now, that's a dangerous argument because this is plotted from 0 up to the peak, which you might think is natural because, of course, at threshold it has to go to 0. But as Sandy said, there's a parton model contribution sitting in here, which is completely independent of alpha S. So in terms of saying, are duality violations small enough? Are these wiggles small enough that they don't affect the alpha S determination? This is a totally misleading figure. Just to sort of exaggerate the situation, if I looked at a different alpha S dependent contribution added into that and plotted rho plus 100 and plotted it from 0 to where it is, it looks completely flat, but it doesn't mean duality violations won't affect the alpha S determination. So Sandy already showed this figure, but again, to emphasize what's going on here, this is what happens when you look now not at this version of the figure, but at this version where you've taken out the parts that are alpha S independent, the parton model contribution. This is what this experimental spectral function, absent the parton model part, looks like. This is perturbation theory, the alpha S dependent part of that. And say I look here at 2 Jev squared. The actual data is 0, so the net alpha S dependent contribution is 0. That's made up of a perturbative contribution and a duality violating contribution that's equal in magnitude and opposite in sign. So here at 2 Jev squared, absolutely for sure, the data tells you duality violation and alpha S dependent perturbative contributions are the same size. Now you might say, oh, well, if the errors are larger here and maybe it's flat, but you've got to really seriously worry that duality violations at this precision level cannot be neglected. Now here's the version, more or less an experimental version of the vector channel case. So in this case, this involves, in the blue points here are the tau Aleph data, and the red points are a version of the isospin 1 part of the R contribution rescaled so that they have the same normalization. This is done by doing a G parity separation. So all the channels that were exclusive channels where you can identify the G parity, you can separate isospin 0 from 1. The ones where you can't, you take 50% each for each with a 50% error, and then this is what you get for the isospin 1 part of R converted to the spectral function normalization. And so you see that, first of all, the duality violating oscillations around perturbation theory are somewhat bigger in this channel, as noted before. But you also notice that now in this region where before the tau data has large errors, and there's a missing point here because XM grace kills a point where you don't have the entropy. So now what you see is it's very clear that, again, like here's a point where we're down at 0. So these are experimental points. The reason the errors get blown up because as you go higher up in the spectrum, there are more states like kk bar 2 pi, kk bar pi, where you don't have unique G parity. There are both isovector and isoscalar contributions. But this is all data with the most conservative treatment of the things that you can't identify as being isoscalar or isovector because of a lack of G parity classification. So these are experimental data for the isospin 1 spectral function out of the R data and the tau data. So this basically, the R data supplements the tau data in the region where the tau data has large errors, tells you that you can really see that there's a sort of nice oscillating, exponentially damped pattern. That's really the case. Okay, so now let me just tell you about the results of the analysis of the R data itself. You already can see that you're not going to be able to safely neglect duality violations unless you go up, higher up in the spectrum. So what we do in this analysis is, first of all, this is just telling you what's the connection between R and the electromagnetic spectral function, well known. The way we approach this is we start with analyses in which we neglect duality violations and do some self-consistency tests. We don't start with S naughts below M tau scored because we already have good evidence that that's not a good approximation there, and we see that again in the analysis. So we start at that and go higher up. Then we fit the parameters. Since we're neglecting duality violating parameters, the parameters are OPE parameters, alpha S, and the relevant condensates, and which condensates are relevant are set by the degree of the polynomial. And then you test the stability of these parameters to both looking at different weights where the same condensates enter and alpha S enters in all of them. Or you now add the asymptotic form of the duality violations, and you try and fit the new things that you didn't determine before from tau, namely some isospin 0 duality violating parameters. In fact, the data is not good enough to be able to just introduce the tau isospin 1 parameters as constraints, then refit them plus all 4 isovector or isoscalar duality violating parameters. So we've had to make an approximation here on the exponential damping and the S-dependent coefficient in the sinusoidal oscillation. And also what we've done is we've worked for the very precise and dense R data in this exclusive region only. I've already basically told you how we treat the OPE parts where we have the OPE or where we have duality violations. We include the small strange mass-dependent contributions, but they make a very small numerical effect. And we do avoid weights that are linear in S because of this observation in renormalon models that Diogo and his collaborators were involved with, that the sort of truncated dimension 0 contributions don't give a very good representation of what you expect the real series might look like for weights that have a term linear in S, so it makes sense to avoid those. We look at this with a number of weights, and again, this is for self-consistency checks. The weight where you just have a constant that has no suppression of duality violations near the point where you worry about them, but if you have no duality violations as your assumption, you only have one fit parameter, which is alpha S. Then here you have a degree weight, a degree 2 weight, which has a single 0 at y equals 1, which is S equals S0, the time-like point on the contour. So that has a single suppression of duality violating contributions in the bad region. Because it has degree 2 and no degree 1, it talks to the dimension 6 condensate in alpha S. And then there's 2 weights with a double 0 at y equals 1. This is the kinematic weight from tau decay, and this is a different doubly pinched weight. This one talks to alpha S, dimension 6 and 8 condensates. This one, alpha S and dimension 6 from this, dimension 10 from this. And so C6 is common to all 3 of these. Alpha S is common to all of them. You can look for consistency tests about whether the C6s that come out of the independent or the different analyses here are consistent and whether the alpha S's are consistent. Okay, this is just an example of a consistency test where I took the 2 doubly pinched weights. I looked at, as a function of what's the lowest S naught in the window that we use, because we, of course, use a range of S naughts in order to help us fit the condensates, because the condensate contributions scale differently with S naught, with higher inverse powers of S naught, up to the end of the S naught that's possible if we restrict ourselves to the exclusive mode RS sum. So these are the results on this side are for the kinematic tau weight. These are for the other degree 2 weight. You notice that if you let your S naught go down too low, you get absolutely terrible quality fits if you assume that duality violations can be neglected. So the fit's telling you don't do that. Then you start getting decent quality fits, and you don't have to look at all this stuff other than to see that these alpha S values match, these alpha S values match, blah, blah, blah. These C6 values match, and I haven't put in the C8 and C10 because they're not common here. But this is just showing you that the self-consistency tests work. Now, this is another thing that you should do, and also this tells you a little bit of extra information. So these are the comparisons that after you've done the fit, and you now put those fit parameters into the theory representation, compare the theory integrals to the experimental integrals, and this is the result that you get just for one particular choice of the minimum S naught in the fit window. Here you see that the experimental integrals have a little bit of an oscillation, and that's in fact a signal of a residual not fully suppressed integrated duality violation contribution because it's the residue of the contribution of the integration over the oscillating duality violating part. So even though the fits say it's okay with W equals 1 to neglect duality violations, in fact you see a little hint that they're not fully suppressed at this lower scale. This is the singly pinched weight, and you see that now you don't really see any sign of the oscillations in the integrated spectral integrals, and these are the doubly pinched weights here. Obviously, you can see that these are very highly correlated since there's no jumping around of the error bars. Okay, so now here, again, I'm sort of summarizing these results and not going into a lot of detail. So now this is just a summary of the results of various analyses with all of the weights, well, actually 3 of the 4 weights, with and without the test of what happens when you put in duality violations in the asymptotic form. So these sets of green, blue, and red points and black points, they all are supposed to sit at the same S naught, and they're just offset so you can see where they are. And so what you see is that up in this region of higher S naught mins, so the minimum value in the window, we always go up to S naught of 4 Jev squared, the end of the exclusive RS region. And especially when you stay away from where you have hardly any points and you're fitting too many parameters, you have extremely good consistency here. But as you go down to lower S naught min, where you would expect the neglect of duality violations to get more and more dicey, it plummets. Now, when you put in this, albeit not as fully fittable as we would like, version of the isoscalar duality violating contributions, you see that these things all go up and become pretty compatible with what you've got here. Okay, so that's the situation. The addition of the duality violations stabilizes the fits in the lower S naught region, and again sort of emphasizes it's almost certainly not safe to neglect the duality violations at those lower S naughts, even though 3 Jev squared is a lot bigger than lambda QCD squared. Okay, the numerical results that we get from this are, it's not, m tau squared is not a natural thing for the electroproduction database, but this is just to compare to the tau results. So the 3 flavor results at scale m tau squared are these numbers here to be compared to what Santi showed from the tau analysis. So of course the central values are in very good agreement. The errors here are somewhat larger than they are here, and those errors are experiment dominated, and so at least in principle improvable. In the case of this, it's less true. You have some significant theory contributions that I'll come back to. This is what happens if you run those up in the standard way to the 5 flavor. Again, they're very compatible with what we saw from tau. An important thing to notice is that in the tau case, the difference between whether you treat the truncated 5-loop dimension 0 series to using fixed order perturbation theory, or you choose your scale as the running scale along the contour, those things differ if you expand the running coupling along the contour. In the fixed scale coupling, those just differ by terms of higher order in the perturbative series, a subset of those. And so this tells you something about the truncation uncertainty, and this is actually not so small in the case of the tau analysis. It's much smaller in this case here, presumably partly because you're working at a higher scale than you did in the tau analysis. And this reduction in this perturbative truncation uncertainty is what helps this to be data dominated, although, of course, the data errors are a bit larger here as well. Okay, so that's the end of part one. There you saw the results of the analysis and roughly what went into it. Now, the second part is to use the RRS data, which allows you to go to higher invariant squared masses S, in order to try and test some of these assumptions about the treatment of the OPE that have gone into traditional tau determinations of alpha S. So, this is the shorthand notation that we're using to describe those approximations, and I'll review what those approximations are in a second here. But the idea is that what's traditionally been done in the tau analyses is you analyze vector, axial, or the sum of those channels. The safest one, because it has somewhat suppressed duality violations, is vector plus axial. You assume that you're at a high enough scale that you can neglect integrated duality violations. To make that as plausible as possible, you work at the highest possible scale, which on average would be true. Kinematic weight, if you have that, it's got degree 3. You have 3 OPE parameters. If you work at a single S0, all you've got is the inclusive width, and that's not enough to determine all 3 of these. So you need some additional input in order to fit the condensates. And the way the approach to doing that was to say, well, let's add some new higher degree weights that involve contributions of this and use those to fit, and hope that there's a sort of effective convergence at low degrees in the OPE so that higher dimension terms scale something like lambda QCD to the D over m tau to the D. And if that's the case, and then you can neglect those higher contributions, then you would get something out of this. But of course, since the OPE is certainly not convergent, and eventually those condensates are going to grow, you have to worry about this assumption. So we want to test whether or not that is a plausible assumption, and I'll explain to you how you do it with RS data. This is just a little bit of information to show you what you're keeping and what you're neglecting that in principle is there when you do this type of analysis. So this is the weights from Pichler-Dibierde that Santi listed before, which go up to dimension 7. And here, if you look at the set of those weights and you ask, what are the contributions in terms of the effective condensates in your S0, here's what they are for each of those corresponding sum rules. These are the terms that are kept for all 5 of these weights, and these are the terms that are neglected. And you notice there's a lot of things that are neglected, and some of them have some biggish factors. So like here, this is neglected, even if you think it's lambda QCD squared over m tau squared between here and here. You've got a numerical enhancement as well. It's very dangerous to neglect these. And the way you would see whether or not it's a bad thing is to vary S0, because these things scale differently with S0. And so if you do a fit where you only keep these things in alpha S, and so your scaling has terms that at most go like 1 over S0 to the 4th, and there's actually something big that goes like 1 over S0 to the 6th, you'll see that when you vary S0. Okay. There's another set of doubly pinched weights that you can also look at that don't, okay, so I should just say that in this case here, when you look at these with non-zero m, that's S over S0 to the m, and so what happens is you strongly suppress the spectral integral, and that corresponds on the OPE side to strongly suppressing the dimension 0 contribution. There's an alternate set of weights called in Peake-Rodriguez-Sanchez optimal weights, which have only always a 1 here, so you never suppress the dimension 0 contributions, so you might say that maybe this is a better choice. And again, this is what the higher dimension contributions look like. These are the ones that you keep. These are the ones that you neglect, even though some of them have some pretty big numerical coefficients in front of them. And it's crucial that you neglect these on the grounds roughly that they scale down. You assume that they scale down rapidly, but you don't know whether that's true in actual QCD or not. Okay, so to summarize what the assumptions that go into this are, the basic assumptions are that if you go to a scale that's something like m tau squared or a bit larger, integrated duality violations can be neglected. And that will be a better approximation the higher degree of pinching you have in the weights, because of the fact that the region near the Minkowski axis where the zeros from the pinches sit is the region where the duality violations and the polarization are largest. In addition, this is a really crucial one, that the integrated OPE series behaves out to the dimensions that you are actually dealing with as if it's rapidly converging. Now, it could be the case that in QCD that's true, and that only when you get to dimension 32 does it start to diverge, but you don't know this beforehand. You have to actually do some tests. So the potential issues are that when you do the standard type analysis of trying to make sure that this is maximally true by going to the highest scale available to you in tau, you don't have the ability to vary S0 and test whether or not it's self-consistent from the S0 dependence to drop those higher dimension terms or the oscillating duality violation terms. And even if you can safely do this, you haven't done the tests to say that the truncation of the OPE is actually reliable. So the way you would do this test, in principle, is by looking at the S0 dependence. But in the tau decay, you're restricted, because if you say, oh, I don't want to go very far below the tau mass, because then I expect suddenly the duality violations to get important, so I shouldn't do that. The problem is, okay, I can't do any S0 variation. But if I go to the RS-based sum rules, then I can, because I can say, okay, you tell me that around S0 equals m tau squared, I can neglect duality violations, and I can truncate the OPE. Both of those assumptions are such that with the exponential damping of the duality violating part of the spectral function and the 1 over S0 power dependence of integrated higher dimension contributions, those things get suppressed as you go to higher S0. So if you tell me that you've got a given S0 where these assumptions work, it better work a lot better at higher S0, and you can explicitly test this with the electroproduction data, assuming you can find a S0 star in the region you're working with where it looks like these assumptions work when you do this type of analysis. So that's what we're going to do, is we're going to use the R data to test this. I see I have 0 minutes, so I think I should get through here without taking all of the question time. Okay, so I basically said what we're going to do here. We're going to look for some S0 star, which should be above m tau squared at least, so that when we do make all of the assumptions in the truncated OPE type analysis, either set of weights, we get a good fit, which would be something that would, in the tau analysis case, would be declared to say that, yes, this is good, we know that this works. Then what we're going to do is, from that point, we're going to get all of our parameters fitted. We're going to then take those, we're going to work out what the theory predictions are for the integrals at higher S0 and see whether or not that works. If that continues to work, then that would be telling you that the assumption that you can truncate the OPE and that you can neglect duality violations is self-consistent. If not, it's telling you absolutely for sure that it's not. An important thing to do, because as you saw already, the spectral integrals are extremely highly correlated, you want to choose things to represent that don't mislead you because of the correlation. So we work with differences on either theory or experimental side, which are differences at the variable S0 and the fixed S0 of the theory or experiment integrals. And then what we'll do in order to assess the quality of theory versus experiment representation is we'll take the difference between these quantities for theory and experiment. So this is a sort of double difference. Okay, so first do a truncated OPE analysis, starting out at S0 equals m tau squared, where at least in tau decay, it's argued that this works well. Now, when you do these truncated OPE fits on the R data, you find at S0 equals m tau squared, very bad quality fits. So this is just an illustration here. You have slightly lower p-values than you'd like. That's not necessarily a surprise, because the hidden strange resonances in the isovector channel, or so the isoscalar channel for R, sit at higher S, and the duality violations are related to the resonance oscillation. So it could be that you don't get into the region where the tOPE assumptions are okay until slightly higher at R than you do in tau. Okay, so then what you can do is say, okay, let me go to slightly higher S0 star and move S0 star up until such a point as when I make the tOPE assumptions, I get a good quality fit, just as I did in tau. So here, for the optimal weight set, that's when you get to 3.6 Jev squared. For the conventional so-called spectral weight fits at 3.7, you get decent quality fits. this is a picture of what happens in terms of standard chi-squared fits, diagonal fits that I don't have time to go into, for either optimal weights or the spectral weights. And you see that when you get up into this region, all of these are compatible, and below they're not, which again tells you the tOPE assumptions are wrong. Oops, okay, I just skipped over a slide. Oh, no, I didn't. Okay, so now if I go to the tOPE fits which at least have acceptable fit quality and ask what is the match between theory and experiment when I go to higher S0, this is if I just plot it in the form of the theory integrals versus the experimental integrals. And if you look at it in this way, you might think, okay, well, you know, these are within errors. This is all basically within errors, mostly within errors. Oh, it's within errors up here at least. It's within errors up here at least. So you might draw the conclusion that it's okay. But in fact, you should be highly cautious because you can see how incredibly strongly correlated these are, and that's also true for the OPE integrals. This is for the similar display for the correlated fits for the optimal weights for a good quality fit. Now what happens if you actually see whether or not there are problems with this by actually plotting this in the double difference form so that you're not being misled by correlations? I don't know why this is displaying so weirdly. You see that, in fact, the match between theory and experiment is really bad. So this is the zero line. I have no idea why it's not showing up. These things just don't match well. And this is also a warning that when you're looking at and assessing how well these fits work, don't look at the other form of the fits because the incredibly strong correlations fool you. This is the same situation for the optimal weight set, and again, the same conclusion is that even above the S0 where you did this apparently good quality fit, the matches are not good. So I'm sorry about these figures. They look perfectly fine on my computer. Okay, so the conclusions, which I got to before I got chased off the stage, of this part of the talk are that first, good chi-squareds from a single S0 fit with truncated OPE assumptions, shown explicitly, it's not enough to actually establish that the tOPE assumptions are good. So you have to look a little bit more carefully because there's such strong correlations. And even if, as I've done in this part of the analysis, you assume that the integrated duality violations are negligible, the truncation of the higher dimension contributions shows up as being inaccurate by this failure to match the S0 dependence between theory and experiment. And it's very important in order to see that that's happening to look at something like these double difference displays. So that's everything. Thanks.
Thank you very much. Questions?
So from your analysis, it seems that you were able to determine the 6-order condensate up to 3 sigma accuracy,
Yeah.
for some of the fit. And of course, all this analysis, they use the weight function such that the dimension for condensate drops out. Now, I wonder if you would pick out your favorite value for alpha S from PDG or for whatever, and you would choose the weight function such that the leading condensate that dimension 4 doesn't drop out, how accurately would be able to determine it. Because the reason I'm asking, because our chairman says that in principle, given the accuracy of perturbation theory today, we shouldn't be even able to determine the dimension 4 condensate, and you claim that in principle you could determine even dimension 6.
I mean, of course, first of all, there's a renormal unambiguity, so this is a truncation-dependent statement, right? Now, truncated with dimension 0 truncated at 5 loops, you can, in principle, say, look at the weight 1 minus y, which would only involve, if you get to high enough S so that you have duality violations out of the game, it would only involve alpha S and C4. So you can do that. But an interesting thing, and I'm not sure whether or not this is related to the ambiguity in the gluon condensate, is that although you'd think that there's an extra 1 over S0 squared dependence in the integrated dimension 4 relative to the integrated D equals 0, and that you should be able to get quite an accurate determination. In actual fact, when you take all of the higher order series in dimension 0 for the dimension 4 condensate, there's quite a strong anti-correlation telling you that you don't get as much of a leverage from that 1 over S naught squared as you thought you might get. So you can get a determination. Now, I did this in the past looking at this with the singly pinched weights, didn't say anything about that, but I think we looked at this because somebody asked us about this, and I think we could only get like 50, 60, 70% determination of C4, but we haven't really sat down and looked at this seriously. We didn't look at this at all for the RS analysis, so I can only give you a very partial answer. But I think there's some caution there in what I remember from my long ago analysis with a student from 2008, which is we were very surprised to see this quite strong anti-correlation between the dimension 4 condensate and the alpha S and the perturbative. And I don't know if that's related to the normal unambiguity, but maybe it is.
Thank you.
So, you could get some sort of a determination of that, which would correspond to some sort of a determination for some implicit definition of the gluon condensate associated with 5-loop truncation in this process. It's not something you could necessarily take over into some other process, that numerical value.
Okay. Any other questions?
So I think that the message is a little bit depressing. That
it is a bit depressing, yes.
That you can never cut the OPE and I don't know. So the thing is that we know, I think we understand a little bit better like asymptotic series when it comes to alpha S expansion, but I think we know very little, right, about truncating the OPE. I mean, we know that it's because I have many, many diagrams, whatever, right? But going deeper and deeper into the OPE, to my knowledge, there's very, very small theoretical knowledge, right? I mean, that would be good. I mean, and you see when there's the alpha S expansion, you can vary scales, and that gives you a hint. I mean, if the mu variation is large, there's a hint that something is not converging, but there's nothing you can vary in the OPE to see what's the mistake that you make because you cut it.
Yeah.
Something like that, like reshuffling the series might be something useful.
But I would say that the situation, I mean, okay, so in tau decay, I would say that what you've discovered is, you say tau decay is a great place to get alpha S because, yes, there'll be some small non-perturbative contributions that I'm going to have to work hard at, but once I get a given precision determination, I benefit a huge amount from the running. So that looks good. Now, I mean, what we're telling you is that the data is saying you unfortunately really can't neglect the duality violations. If you were at a high enough scale that you could neglect those, the fact that you've got OPE contributions, the finite energy sum rules are a sort of funny transform that transforms you from Q squared to this variable S naught, and which knocks out or heavily suppresses higher dimension contributions. So this helps you with the asymptotic eventual divergence of the condensate series. So if you're at high enough S naught that you can neglect duality violations, you can fit those effective condensates. So that would be a good situation. Now, unfortunately, God was really mean and gave us a tau mass that's a little bit too small. And so that means that at present anyway, all we have in terms of what we know rigorously about duality violations is the asymptotic form, and we have to assume that that goes down into the tau kinematic region. Current data says that that's compatible with that assumption is compatible with the data, but we're working with old data from the LEP experiments, and the reason you have large errors near the endpoint is that the statistics in those bins near the endpoint are very low. And the B factories could have done a much better job because they have 1,000 times the statistics, but manpower means that that's not going to happen, except maybe at Bell 2. Now in electroproduction, you're in a better situation because there you have the freedom to vary your S naught that's unrestricted by kinematics. Now, it would be ideal if we had better inclusive RS data above 4 Jev squared, because right now you're basically dominated by Bess and Keter. Keter has much smaller errors, but in the KNT fit, in fact, the fitted values actually are closer to the Bess because of certain correlation effects in the fit. And right now, it's either there's continued duality violations in that region, or actually the Keter data is more accurate and you're more or less perturbative above there. We don't know, but if you actually got better data there, you could go to even slightly higher S0. And you saw already the signature that the duality violations, the exponential damping, is damping out those integrated duality violation contributions fairly rapidly as a function of your upper S0. So it wouldn't be that much higher up that we would need to get, I believe, before you would be in a much better situation. So, we'll have to see, but there's at least a chance of improvement. But, I mean, a take-home message should be that you have to pay attention. If you want to use these determinations of alpha S as part of the precision determinations at MZ, which of course is typically the second most precise after the lattice, there are some non-trivial aspects about residual non-perturbative contributions that are associated with the fact that these observables are things that are not leading order in alpha S, but the alpha S dependence comes only at next to leading order.
Okay. Is there any other questions? I don't see any, so let's thank the speaker again. And we resume in 20 minutes at 11:30.
That was a very long answer.
Yeah, but I mean, it's a relevant question.